Okay. So we are recording, I guess. Yes. So please be regular. I have planned to. So first of all, hello. So we are recording now. So I am Moina Viswas. I was a 2021 Jadavpur University graduate, and then I joined into IAS as a PhD student at the BCD program, and I've been awarded the Prime Minister's Research Fellowship, which is the reason I'm here back teaching my juniors. It's a fellowship where we have to do research and then get to interact with young students who want to join or academia or learn something new for developing their skills. So that's why I'm back again at my alma mater and interacting with all of you. So I hope will be very interactive and will learn a lot, both me and all of you, through the journey over the next few months. Uh, so I'll get started. So this course would be on reinforcement learning, but for the first couple of classes, 3 classes, all I'll say is reinforcement learning is the method in which all living organisms or agents learn in this world. So they interact with the world using rewards. The world tells them which is correct, which is wrong, and accordingly they choose policies. So that's what we'll be learning in this course. How do we generally learn that? But for that, we need some foundations in probability, which is the most important fundamental building block of reinforcement learning, because everything that you would be doing would be probabilistic and random and so on. So yeah, we'll get started with first 3 sessions. Roughly, I have planned to be on probability, where I'll be discussing random variables, distributions, and joint distributions. Although this was a prerequisite of this course, I I think I'll be giving a quick recap, and which would be self-contained to understand the course in itself. And whenever I give some reference to go back and see, I'll hope you'll put some effort and solve the questions and so on. Okay, so I'll start off. If there are no questions, I hope if there are questions, please stop me, else I'll start. Okay, I'll get started then. I'll try to keep it short today, and then we can keep as we go longer into deeper into the course, we'll have it more detailed quick sessions. So okay, so today we'll be talking about what is the random variable and some distributions and what is expectations. So first of all, to understand random variable, we have to understand what is a random experiment, and then understand probability as you understood in class 11 and 12 and so on, and then we'll get into what is random variable. So what is a random experiment? So for example, say you flip a coin. So you have a coin and you flip it. So this is a random experiment because you don't know what the outcome of the coin is going to be. So ranging from coins to the what the stock market would be tomorrow, to a behavior of particles in quantum mechanics, effects of medicine on patients, everything can be modeled using a random experiment. Say if you have success, failures, and so on, could be outcomes of the random experiment. For example, if you have a coin toss, head and a tail are the outcomes of the random variable. Of not sorry, a random experiment. So head and tail are the outcomes. So we understood what is a random experiment, anything whose output is not deterministic. And could be, so we could have multiple. For example, like on an experiment of a coin toss, you can have either heads or tails and so on. So that's why it's called a random experiment, because the outputs can occur at random. So now that is clear. So what is the fundamental building block of probability? That is known as a sample space. So sample space are all the possible outcomes. They are possible outcomes of the experiment. So if I ask this, what is the sample space for a coin toss? So for example, I'll ask you, say I toss two coins. Two coins. Sample space. So this is, say, let us denote this as the experiment E. And we denote the sample space for the experiment E as, say, sigma E. So sample space is generally represented as sigma and then sigma of E. So can you tell me what would be the sample space of this experiment? Anyone? They are the all possible outcomes of this experiment. So I've tossed two coins. So what are the possible outcomes can I get?
Head, tail, and like that only.
Okay, so you will get head, 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 tail, head, and
And
tail, tail, right? So this is known as the sample space. That's very clear, I guess. Similarly, if you roll a dice, 1 to 6 would be the sample space of the experiment. Now, that is the first definition that we'll have to keep in mind. The second definition is event space. So generally, event space is a bit non-trivial, but for the sake of ease and intuition, what we'll be considering the event space to be is the power set of the sample space. Power set. What does it mean? So event space is generally a subset of, so event space can be anything, but it is generally a set of subsets of omega. So sorry if I said sigma, it's omega, right? So set of subsets of the sample space. So one of the samples subsets could be, so that has some properties, but what we'll be considering is the power set only. That is list of set of all subsets. I don't think we'll be needing anything other than power sets in this course. So I'm not going into measure theory or sigma algebras. So we'll be dealing with simple ideas. So that is generally represented as F. So it's the set of all subsets, say. So how do you define set of all subsets? Can you tell me here? So why is it defined as 2 to the power sig omega? Because for every element in the sample space, you can either take it or not take it. So it will have 2 to the power omega number of elements. That's why the power set is represented as 2 to the power omega, right? Any questions? So how many elements would this set have, this set F, if you have any doubts? The set of all subsets. So you can make subsets by either selecting an element or not. Is it clear? So how many of them can we do? So if there are, say, the sample space has a length of omega bar, or this is the length of the sample space, how many subsets, how many elements would the set F have? So say head, we can either select head or not select it. So how many options per element? To select, yes, or not select. You have two options per element. So by simple counting, so you have 2 into 2 into 2 omega times. That is 2 to the power sigma, right? To the power omega. Okay. Okay. So let us write this down. It will be easy for you to understand. So give me one element of the sample, the event space. The first element.
Head.
Okay. So Can this be an element as well?
Yes, empty set is can also.
Yes.
Because I did not
16
select anything. If
elements.
I did not select anything, and then I think Somudeep said head head. So I'll put head head in. Then all the singleton sets I can put, right? They are subsets. Yes or no?
Yes.
Okay. Then I'll put all the two at a
Elements.
time sets.
Yes.
Yes. So 2 at a time and so on. So let me write it down just for completeness. So how many 2 at a time sets will you have? Anyone? How many 2 at a time elements would you? Yeah, force choose 2. So 1, 2, 3, 4. So I have got how many? 1, 2, 3, 4, 5. Tail head, tail, tail head, head, tail, tail. And then 3 at a time, right? I'll have 4 of them, right? 4, 3 at a time. And then the entire set, right? So there are 16 of them. Okay, great. So we understood what is a sample space and what is an event space. Now, the definition that you studied in school days of what is a probability of an event to occur. What was the definition that you studied? That was a naive definition. What was the definition? It said that it is the number of favorable outcomes by total number of outcomes. So number of favorable outcomes by total number of outcomes. People who are asking me to join, please join the Teams group. It will be easy for you to join instead of staying back in the lobby. Sure. So it was the number of, for example, naive definition. Say probability of having at least one head in a coin toss. What would be the, what would it be? What would be the probability be? One head, at least one head in 2 tosses, I meant. The previous example that we saw. Anything?
3 by 4.
At least 2 heads. At least one head, sorry, in 2 tosses. So this is the size of this set. Head, 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 tail, and tail head, right? The size of this set by total number of the sample space size is 4. So this is 3 by 4, correct? But this naive definition of probability has a problem, inherent problem in it. The problem lies in the fact that it overly depends on the outcome of the experiment and assumes all outcomes are equally likely. So which may not be the case. For example, I'll give you a ridiculous example. Probability of a human jumping from Earth to moon. So if I use this definition, naive definition, say let us take this as event E or experiment whatever E. So can you tell me what would be the probability be according to the naive definition? That a human can jump from the Earth to the moon? Half. Because yes, size of yes by yes or no. Because you can either jump to the moon or not jump to the moon. So those are the two outcomes that this experiment can come up with. This will give you half. So this is where you can clearly see where the experiment, where this definition fails. That's why we developed the entire theory on probability. Because all events are not equally likely. So generally in probability, what we do is, so you remember the event space, we define a function from every element in the event space to a probability. That is called a probability measure. So why is it called a measure? I'll not go into it, but it's called, you can think of it as it is a function. So P is a probability function from the event space to 0, 1. Right? So for example, in this, I could simply say this function that yes to jump could be 10 to the power minus 20 or something like that. I can define it like that, right? Very low probability. So we define it between 0 and 1, where 0 is impossible and 1 is certain, right? So it's a mapping from the event space to the probability set, which is 0, 1. Is this definition clear of a probability function?
Yes.
Is this definition? Okay. So this is what you define a probability function to be. So in generally, theoretically, probability space is defined as sigma, the omega, the sample space, the event space, and the probability measure. So this is on the event space. So this is a 3-tuple, but we're not going to this, but basically you must remember that first comes sample space. Event space is all the possible subsets of the sample space, and the probability measure is the probability function that maps from the element of each of these subsets to a 0, 1. So for example, when we did this example that naive using the naive definition, do you agree this head, tail, and tail head is a part of the, do you agree that I'll just write it over here. Head, tail, and tail head belongs to F? Or the event space? It belongs to the event space, right? It's
Yes.
one of the element. It's a 3 element. So here it will be head, tail, head. And we say that we define the probability function. It's a definition rather than counting as 3/4. Instead of calculating it this way. We'll see. As I gave you an example where this is equiprobable, so we took it to be 3/4. Otherwise, we will have to recalibrate our probabilities. I hope that is clear. Any questions you ask me, I will go into. So we have discussed the naive definition, problem with the naive definition, random experiments, sample space, event space, and what is a probability function. Now I'll discuss some properties of the probability function, and then we'll solve a couple of questions using those properties. Okay, fine. So 3 properties, if you look to the left of the screen, the axioms of the probability function. Say given a set of mutually. So currently, let's set of events AI. We can say that probability function is always non-negative, right? This is the first property. These axioms in mathematics are the starting point of deriving your theorems or lemmas or propositions. So these are truths that we don't question. So this is by, you can think them as axioms, that they are used to derive other theorems. Okay. So, but they have to be rational. Do you agree that every probability has to be non-negative? So this is a good assumption to take, not causing any problem. Then another assumption is the probability of the entire set occurring. So the probability that an outcome would occur in the entire sample space. What is the probability of that? Outcome in the sample space. That is by definition one, right? Because by definition, a random experiment's outputs can only be in the sample space. The sample space is defined as the outcomes of a random experiment, right? Because one is we are taking a certainty. Do you agree? Okay.
Yes.
Let us. I'll just write it over here at the end. Okay. So probability of any event an is greater than 0. This we have explained, non-negative. Similarly, the probability of the sample space is equal to 1. Why? So if you consider this Venn diagram as the sample space, any outcome of the random experiment would lie inside this, right? So any outcome, say omega is a small omega is an outcome. By definition, omega belongs to the capital omega set, right? Which is a sample space. So for example, head comma tail, I'll just give you an example. Head, tail, tail, head, the same example we are taking. So if I tell you what is the probability that any of these events occur, that's the probability of the sample space to occur. That is clearly 1, right? 4 by 4. If you have any doubts, please feel free to ask. The third axiom is if ANs are mutually exclusive. So these are mutually exclusive. What is mutually exclusive?
Intersections and
Okay, intersections is so just
Not
there are
dependent on each other.
yeah, they are not. So I'll define it. So let us draw a mutually exclusive set. A1, A2, A3. So which means that A1 intersection A2 is equal to the empty set. Similarly, AI intersection AJ is the empty set for all I not equal to J. So if I and J are not the same, so they will always be empty. So can you give me a reasonable axiom to tell me what the probability of this should be? So if say this probability of this set is P of A1, the probability of this is P of A2, and the probability of this is P of A3. So what would be the probability of their union? Can you give me a reasonable?
the sum of their individual probabilities makes sense.
So this is a measure definition. So but we'll assume it to be. So this is the sum of the individual probability. Good. It's a good assumption to have. So because this is what is actually happening, we are taking union of the three. So you can think of it as we are making a big ball. So I'll just give you the intuition. So when they are individually there, think of them, they have some mass. They have 5 kg, 10 kg and 11 kg and so on. But they are different masses, right? So if there are different masses, you add all of the masses together. So you will get the sum of the masses. If they had common mass is like two balls mixed together, then you would not have the same equal mass, but some of the individuals. But here you would have, right? Because they're all individual. You just add up their weights. That's the idea. So, but yeah, this was what we were discussing about the axioms. Now let us go back and prove a few theory results. Okay, so let us prove this first result. So this is very intuitive, right? So the first result that we'll prove is P of phi is equal to 0. Can you tell me what is the intuition behind this? Or the proof, what will we use? I know something about certainty.
So we can
Don't call me
use
sir,
the
please.
fact that the intersection between the entire sample space and the phi subset is empty. So we can break the fact that P of omega equals to 1 into P of
Okay,
omega equals to P of phi
good.
plus P of omega.
Very good. So, so omega can be written, do you agree, can be written as the union of the empty set and the omega set, right? Do you agree?
Yes.
Yes. Good. So, and these are mutually exclusive by definition. So I will use these properties. So P of omega is equal, I'll take the measure on both sides. And what will I get? I'll get 1 equal to P of. So this is how, why am I doing this? This is trivial, but this is how you generate an aptitude for proving mathematics. So up to 11 and 12, a lot of like junior students here who have not done a lot of proofs, but proofs are very important to understand concepts. So to increase your logic, which will also be useful later on if you are applying for GATE and so on. You can, yeah. So fine. So so this again on the right side by certainty, the property is 1. So P of sigma is 1. P of phi is 1, 0, sorry. Right? Hence proved. This is the first proof. The second proof says that P of A is
Excuse me,
less
sir.
than B. Yeah.
Won't we be using the third axiom as the infinite series, or will we just using the finite case?
Finite case in which one?
In the third axiom,
It
I
is
have
an
generally read
infinite
it.
case. Like
Yeah.
it is right. You're right, Shohrudin. It's the infinite summation, but those are like if you take n tends to infinity, that can be shown to be the infinite case. And also, if you take the finite case, so that's a very measure theory idea. But if the reason I took it is to be finite is because everything we'll be doing is infinite, and when if I get into infinite thing, I'll have to this is one liner. So if you have an infinite set, all we need to do is take a union with every set that is like 5 is 5 here, right? Which is an empty set after a particular n, and then we get the corresponding to the third axiom that we selected, right?
Yes, yes. Just then we have to put this assumption on the probability measure that it the series has to converge. Any
That
infinite
is true.
series which is probability of disjoint events has to converge.
Correct. Correct. So this we are assuming to be a good. So since it's a measure, so I'm not going into measure theory. That's the only reason I'm not going into it. But measure theory, by definition, it will converge. That's the idea, and this itself will be a outcome of that. Is that okay, Shobhit?
Okay, sir. Okay.
Please don't call me sir. You can call me Moinak or Moinakda if you are. I'm just
Okay,
a
Dada.
few. Yeah. So if you have any particular questions regarding this measure theory, I can help you out, but we'll do it offline because there are a lot of people last time I got a feedback that too much of theory would like really getting them a bit non-interested. So we don't want the class to be emptying out. But in the Teams group, you can write out your message. I will respond to it. Sure.
Okay. Thank you.
Okay. So the second question that I have for you is prove that P of A is less than P of B if A is a subset of B. So do you have a proof for it? Anyone?
Oh, obvious.
Yeah, it is obvious, but we have to write out a proof. Can you
We
tell me?
can write it
Formulate
as
it.
the sum of P of
Okay.
A plus P of B minus A, and because every probability is greater than equal to 0, so the
Good.
different
Good. Very nice.
difference would also be greater.
So we start off with B without A and A. If you take union, they would be equal to B. Do you agree? And then these are mutually exclusive. So probability of B without A plus probability of A is probability of B. Very good. So now this is greater than 0, which means probability of B is greater than probability of A. This is a very important property, also known as the monotonicity property. We'll be using it a lot. Okay. So this was a bit, I hope you have an understanding. I see that a lot of people have understood it. That's great. Now let us get into a bit more advanced stuff, which we will be generally doing throughout the course, that is discussing conditional probabilities and so on, because entire RL is just conditional probabilities. So let's get into conditional probabilities. And for that, we need to understand this formulation. So this is again a definition, but I'll try to intuit the reason for this definition. There is not a, so the proof is very sketchy and not very rigorous, but yeah, it's convincing. Let's look at it. So it says that given an event B already occurred, what is the probability that A occurred? So we have to show that. So this function P of A given B means that an event B has already occurred. Say in a coin toss of 4 heads, two coins, one head has already occurred. So what would be the probability that the next would be a head? Something like that, or something like so. Say we have 2 coin tosses. The first coin toss is given to be head. What is the probability that you will have two heads? That's the idea, right? Normally you would have. Did you get the questions? So I'll maybe do that, but yeah, is that clear? Is the intuition clear? Given that B event already occurred, what is the probability that A occurred? Is the definition of a conditional probability or a conditional event probability of an event. So let us see. Look at this Venn diagram, A and B. What did I say? I said that B has occurred. So do you agree that what is the probability that A will occur? Probability of A will occur. It must be in this intersection. Yes or no? Because B has already occurred, my entire set A minus B can be removed, right? If B has already occurred, my entire set A minus B can be removed. Okay. So do you agree this will be proportional to A intersection B? Why am I saying proportional? This is because we have suddenly left out a lot of space in the entire probability space. So B has occurred means our new space is just B. Now, how can we find the proportionality constant? Can you tell me? Is it clear, or do you want me to explain anything in particular? So can I take A equal to B? If I take A equal to B, so what will I get? I'll get K probability of B equal to So let us take the left-hand side, for example. So probability of B given B. What is the probability that B has already occurred? What is the probability going to be?
1.
Very good. This is going to be 1. Just a moment, it's getting great. And what would be the right-hand side going to be? This is the LHS. The RHS is going to be from K into probability of B intersection B, right? Which is K into probability of B. So I can say clearly that K into probability of B is equal to 1, which means K equal to 1 by probability of B. So I get this as 1 by probability of B into probability of A intersection B, right? So this also we have shown the Bayes rule, the conditional probability. So let us take an example. I just came to my mind. Let's take an example of a conditional probability. We'll do a lot of them with conditional, more detailed questions, but let us take an example. Say first tell me probability of, again, 2 coin tosses. They are fair, assumed to be fair. Probability of head comma head. What is the probability of head comma head? The first one being a head and the second one being a head, right? 1 by 4. Do you agree? Now I say that probability of head comma head, given that the toss 1 was equal to head. What will it be?
Half.
Very good. So T1 equal to head, T2 equal to head, which means that probability of T1 equal to head was it disconnected or something?
No.
So okay. So the numerator is 1 by 4, the denominator is half, right? Probability the first toss being head, so we get half. So this is how events, given a particular event occurred, can actually give you more information. Say, for example, if I say that, I'll give you a very intuitive example. Say, today they say that there are a lot of black clouds. So given that there are a lot of black clouds, you'd say that there's more likelihood of rain coming compared to if there was a clear sky. So these are how events interact with one another. So I have a question for you all. Can you tell me, are mutually exclusive events independent? Okay, we'll come into independence. First, let us, no, sorry. I'll come to it. Sorry. Okay, now let's get into the what is known as Bayes rule, which is the heart of entire statistics and probability. That is how do you change conditional distributions? So you write one conditional distribution in terms of the other. Say, I know the conditional distribution B given A. Can I rephrase it in terms of A given B is the question, right? So I know that probability of A given B can be written as A B, which is whenever I write A comma B, you think that this is an intersection of A and B, both events, into probability of B by probability of B. So now the numerator, can you tell me what can I write it as? So if I have to prove the right hand side, Any idea? Can I write this as, so if you see this equation of conditional probability, I can write A comma B as probability of A given B into probability of B, right? Okay. Similarly, I can write probability of B given A as probability of A comma B by probability of A, which means probability of B given A into probability of A. So the basic trick to remember this or do it fast rather than proving it every time is to, whatever you condition on, you multiply the marginal distribution of that. So for example, I'll tell you what these terms are. B given A into probability of A, right? Fine. Okay, if there are no questions, I'll advance. This is basic stuff, but yeah. So this is known as a marginal. This is known as a conditional. And in machine learning, this is often known as posterior. But yeah, so people in this world think, why is it called a posterior? And why is it called conditional and so on? It is because if you see that people update, so posterior is updated. So there, if the conditional exists and the marginal is given to you, so you update your belief based on the conditional distribution. That's the entire idea. That's why it's called the posterior distribution. After observing some data, which is B given A, you update your belief. That is A given B. I'll give you an example of a question that will help you to understand this or better appreciate why posterior conditionals and so on. Okay, so now two events are said to be independent if given B, we don't get any information about A, right? That is, the probability of A given B is the same as probability of A, which also means, can you tell me how do I prove this? From this above statement? Am I audible?
Yes, just put the definition of the conditional probability and multiply both sides by P of B. Sorry.
So okay, that's fine. So, or I can just convert this joint to like this, right? You're saying multiply both sides by, wait one moment. Okay, P of this, and just I take this to this side. That's right. P of A given B, P of B is equal to P A comma B. And this is already told independent, so that is P of A. So remember this very well. We'll be using this throughout the rest of the course very, very rigorously. So any time two events are independent, for example, two coin tosses, as I was saying. So probability of head comma head can be written as probability of head into probability of head, which is half comma half, which is also matching to your 1/4. So this is a conditional. This is known as a independent event. Two events are independent if only their marginal distributions will come to what marginals are product. They can be represented as products. Yeah. So that is one. Then last thing before the last revision of your class 12 stuff is the law of total probability. But people get confused with it a lot. So I'll just please bear with me for doing this as well. Say there is an event B. This is the event, say. That is, that do you have, right? So my question to you is, can I write this B in terms of all the other A's? So what are A's here? So if your list, so A's here is known as a partition of the sample space. So if the entire sample space is given to you, the A's would partition the sample space. What does partition mean? Partition means that this, I will erase this. So you can remember this diagram, and this would solve all your problems of partition ever. So this is like you have this entire tile and you partition it into subtiles so that no two subtiles are going to be overlapping with one another. Right? So first of all, first condition is AI intersection AJ is equal to the empty set for all I not equal to J. And the second condition is the union of AIs is equal to the union of AIs is equal to the entire sample space. So this is how you define a partition. So now I say that given a partition, the law of total probability tells me that you can take the intersections of each of these elements in the partition with the event B and then sum the AIs out of it. So we'll be seeing how effectively we'll be using it in later when random variables come in. But this is very important. Just can you tell me how do you do that? We can use the axioms that we already have. So what can I say? I can say B can be written as, I have already done this. So B can be written as B intersection the omega set, right? Or the sample space, right? And then I can write B intersection the unions of, I'm putting the partition definition over here, AIs, right? Now, what can I write this further? So let us draw it once. So the intersection of B with respect to each of these AIs. So do you agree that this will be B intersection A, say the kth element, right? So can I write this as, so if you are silent, I'll assume that you're understanding. I think you are. Is this right? So I just use a distributive property of intersections and break it out. And then use probability on both sides. Do you agree that AI intersection B intersection AJ intersection B is equal to phi for all I not equal to J? Can you tell me why? I mean that these are exclusive events. Also sometimes known as, when partition is also known as an exclusive and exhaustive event. Can you tell me why it's going to be in the empty set? Very simple actually. So
because AI and AJ are exclusive.
okay, so let us define this as EJ and this as EI. So if an element, say let omega belong to the intersection of EI comma EJ, which means that omega belongs to EI comma omega belongs to EJ, which further means that omega belongs to AI and omega belongs to AJ, which is a contradiction, right? Because AI and AJ are exclusive. So these are the small little proofs that I'm doing for you to like get familiar with proofs. But yeah, this is the proof by contradiction. So this can be written as I equal to 1 to k probability of AI intersection B. This is the law of total probability, or again, you can remember this in this format. So probability of B is the summation of all the partitions that you have of AI comma B. So you are actually summing out, or this is called marginalizing over events of AI that cover the the sample space. Fine. This will be useful later on, but yeah, just remember that we have summing over all A's and only B remains. So this is a good way to remember. Fine. Now, a question that I was asking you before I get into this intuition of priors and posteriors is, are mutually exclusive events independent? If yes, why? If no, why? Say A, comma B are exclusive events. Events, that is A intersection B is equal to the empty set. Can you tell me? Independent as in A given B, is it equal to P of A? First, give me the mathematical proof and then give me the intuition. See, first of all, I can easily write down the mathematical.
No.
Yeah. Yeah.
Will the answer be no?
Answer is no. Who said this first? I couldn't get your name. Could you tell me your name and then answer? I can't see you because there's a lot of people here and can't. Okay, not tell me. It is no. You are right, but tell me why.
Like P of A intersection B will be
Oh,
PA
right.
into PB, which is non-zero.
Yeah, correct. So P of A intersection B for this exclusive event is clearly the empty set, which is 0, which is not this, need not be the probability of A. But the intuition of this is very simple. So they are not independent. People often think that exclusive events are independent, but they are not, because in the Venn diagram, they look to be outside one another. So they are not independent. It's like quite dependent, because if B occurred, right, A will never occur, right? Because they're exclusive. Yes or no? If B
Yes.
has
Yes, sir. We
occurred,
also have to assume a little bit that those are non-empty events or with
yeah,
probability 0.
like it's any event. Like this is for any event. So this is the probability of A is not equal to 0. Those are correct. But this is like for any trivial in any case. So if it is any case, so the proof goes like this. So if it is going to be true, it must be true for everything. But if it is not true, then you can just show one counter example. That's what I showed. Is that fine?
Okay, sir.
Yeah, don't call me sir again. Fine. Now, this example, a very nice, simple example to understand priors and posteriors. So I say that let there be a test for cancer is 98% accurate. Given a person tests positive, what is the probability that they actually have the disease? Given that cancer in an individual can only occur, say, at 1 in 1,000. So first of all, it's given that the test is 98% accurate. That means, what can I write down? Can you tell me some conditional distributions that I can write down? Say C is the event when cancer truly has cancer. Let us put T as the event tests positive for cancer. Can you tell me from this 98% accurate test, what can I write down? And we are assuming no equal number of false positives and false true positives, if that is a question that somebody is wondering. Yeah. Go ahead, Saptarshi. Yeah, Saptarshi, you wanted to say something? So I know that given cancer, a person is cancerous, the test would be. Do you agree? This is the right. This is one of the correct things we will get. Given cancer,
Yes.
the test would give positive outcome 98% of the times. Similarly, given not cancer, the test would be again 98% times would tell me that it is not cancer. We are assuming that it is balanced accuracy, not real accuracy. Balanced accuracy means for both corrects and positives and negatives, both are. So I'll just write it down in case to be less sloppy. Both positive and negative predictions are equally accurate. Fine. So, so what is the question that we are asking? That given that a person has tested positive for cancer, what is the probability that the person is actually going to have cancer? So what are we trying to do? We are trying to find out the C given T, right? This is the question we are asking. Given the test is positive, what is the probability that the person has cancer or not? Okay. So what can I write this as? I can write this as, I don't know this. So what can I write this as? I can write this as probability of T given C I know into probability of C by probability of T, right? By Bayes rule, right? So the numerator, I think it's lagging a bit, but yeah. Can you see?
Yes.
Okay. Fine. So the numerator, I already know it's 0.98 and probability of cancer in a person is 10 to the power minus 3. But the denominator has to be found. And how do we find P of T? That's why we did. We are just putting everything together, Bayes rule and law of total probability. Anyone? So what do we have to generate? So to find probability of T, what do we have to do? By law of total probability, we have to create a set of events such that union of AIs is equal to the entire sample space. So can you tell me what would be AIs here, which would help me? This is law of
C
total
and C.
probability. Very good. C, comma, C prime. That is having cancer or not having cancer. This can be written as probability of C intersection T plus probability C prime intersection T, which can be further written as, what can we write this as? T given C into probability of C plus T given C dash into probability of C dash. Can you fill in the numbers? First number is 0.98 into 10 to the power minus 3. What is this number? So the probability of T given C dash is 0.98. So similar laws of probability hold even for conditional probabilities. So what would be the complement set given T dash? Yes or no?
0.0.
This is 1 minus the probability of T given C. Same law. So 0.02 into the probability of not having cancer is how much? 0.999, right? Probability of C is 10 to the power minus 3. Probability of C dash is 1 minus 10 to the power minus 3, which is 0.999. So if you substitute these values, you will get probability of C given testing positive is around 0.047. So even if you test positive, you only have around 4% chance of getting cancer. This is what, so that this is why this is called a posterior distribution or a posterior probability. Because you are updating your belief every time. The belief that the data is, where is it? Yeah. The data that you have is of the test. And given the test, you are trying to update whether you're going to have cancer or not. So here, every time you're getting cancer, you see 98% of the times it is going to be correct, which is already given to you. And using the priors, you tell me, you update your belief that if I test positive, what is the likelihood that I'm going to get cancer? So last time when I taught this class, I had given an example of Sally Clark, which was a very interesting case where a mother was convicted of killing two children, her babies, but just by using the wrong conditional distributions. Like, for example, C given T, we found out to be very low. The lawyers used, for example, here T given C and showed that the probability was very high. And since the judges did not know probability properly, she was convicted to death, like in life imprisonment. Only after a long time when statisticians came in with the priors and all, did she get released. So it's very important. We live in a world where we update our beliefs using what we see. Therefore, this is a very important to use Bayesian Bayes rule. Okay, so now coming to the second half of our session today, what is random variable? So now we have understood what are events, what is the sample space, and so on. Now let us get into what is random variable. I'll just do 2 or 3 random variables today, 3 discrete random variables, and we'll continue with continuous random variables next day. So it's going to take like 30 minutes more. Okay. So what is a random variable? A random variable is in simple terms is a mapping from the sample space to the real number line. So why do we do that? It is because it's easy to calculate, make a lot of calculations, which you'll see now. It's difficult to deal with complex sets, but for example, heads and tails. But if we say that the random variable x is the function and which maps from head to 1 and tail to 0. Now these numbers, we can do a lot of computations with these numbers. For example, we can just say out of 50 coin tosses, what is the number of heads you're going to get? So you'll get the sum of all this as the number of coin tosses, number of heads you're going to get. So things like this, computations become very easy. That's why we have to map. What we do is random variables are defined as functions that map from the sample space to the real number line. Right? So that is a good definition to have. But for example, I gave you for head, you had an output of 1. For tail, you had an output of 0. But remember, the probabilities are defined on events. So generally in the books, you will find that you will see something like this. This is also known as a PMF, which will come to probability mass function. But what does probability equal to k mean? Like say a random variable taking a value 1. So what does probability equal to 1 mean? See, probabilities are defined on what have we defined now? The sample space, the event space, and the measure of the probabilities on what? P is on elements of the event space, right? Do you agree? So, but what is this weird operator that I have, which I have to use probability on? X is equal to 1. Is there anything random about X? So if you observe, if you're following what I'm saying, X is a function, right? So if X is a function, if I give head to the X, it will only give me 1 always. So there is nothing random about the random variable. Nothing random about the random variable. Remember that. Because random variable at the end of the day is a function. So, but then how are we defining probabilities? If there is nothing random, it will always be either 0 or 1, because it will either going to happen or not happen by deterministic. But by writing x is equal to 1, we mean that we are talking about this set. The set of omegas in the sample space such that x of omega is equal to k. Also, we define this set as x inverse k. So I'll give you a diagram. Say this entire ball was, so let us define this as B, was mapped to this number k. So x inverse k would be equal to B. Do you agree? First of all, functions can be many to one, right? So many values in the sample space can map to the same value. Yes or no? I'll give you an example. Maybe that will make it easy for you to understand. Is that okay? Two things we have understood. One is it's not random. Random variables are not random variable. Is nothing is random about the random variable, and the whatever probabilities or the outcomes the random variable is taking is actually an inverse map to the sample space, right? So let's take an example. It will be very easy for you to understand. Let's take a die. We roll a dice. Roll a dice, right? So when you roll a dice, I define this random variable as x of 1 is equal to 1, x of 2. Let me draw the mapping. 1, 2, 3, 4, 5. Okay, the outcomes of a die. And then I map it using x, something like this. So this is my sample space, and say this is my range space. Say x of omega, let us write this as. So 0, 1, and 2. So these are the three outcomes. For 1 and 2, I put it through 0, 3, 4, 5, I map it to 1, and 6, I map it to 2. So now if I ask you the probability of x is equal to 1, what will you say? Can you tell me? Are you following? I roll a dice. The sample space is 1, 2, dot, 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 6, right? I define a function which maps from this to 0, 1, and 2. And then I ask you what is the probability that x is equal to 1, the random variable taking a value equal to 1. Can you tell me?
Half.
Yeah, 10.
The probability of the
3/6.
event 3, 4, 5.
Okay, others, are you following? So this is as we defined omega, all the events in the set such that x of omega equal to 1. So for next time, I will not be writing this. So that's why I'm trying to get it into your head, because for proofs, you will need this definition. So which is again x inverse of 1. Now what is x inverse of 1? Which set is it? Any other than Saurudhi and Saptoshi, anyone?
3, 4, 5.
Very good. So it's you go backwards and you select all of these 3, 4, 5. So now again, if it is a fair dice, it's 3 out of 6, that is half. Right? Clear to everybody? Fine. This is what is a random variable. I hope I could explain to you. So now we have understood what is a random variable. Now let us look into how we use these random variables. Let's understand the building blocks of random variables, which are distributions of the random variables. So first of all, which I'll talk about is a Bernoulli random variable, which is the fundamental. All this while I was talking about the Bernoulli and you didn't realize, maybe if you have not studied, a Bernoulli random variable is a random variable which either takes zeros and ones. Right? So for example, a coin toss. Bernoulli is equivalent to a coin toss. where the probability of head, say x is equal to 1 is equal to p, and the probability of x equal to 0 is equal to 1 minus p. So x is then said to be distributed as Bernoulli p. See, random variables and distributions are complementary things. So without distributions, you can't have random variables, and without random variables, you really can't have analyzed distributions, and vice versa. I meant the other way around. Without random variables, you can't have distributions, and without distributions, you can't really analyze random variables. Yeah. So, okay, so this is fine. So x is distributed as Bernoulli p, then it is a random variable. This is the random variable. For example, say if I said head, so this again, to reiterate, this x is equal to 1 is often said to be the event, some AP event, the positive event, right? So the AP event is the event where of success. So whenever success happens, so x of success, say we say is equal to 1, and x of failure is equal to 0. So similarly, we can define for coin tosses and so on. So this is the definition of the PMF, the mass function. Any questions you can ask me. By definition, the probability of success is P, and the probability of failure is 1 minus P. Then the random variable x is distributed as Bernoulli P. Now I'll do a question for you, and then we'll see how to manipulate these random variables. Okay, so mass function we understood. So another particular function which comes up will be more useful to all of us would be the distribution function, or the cumulative distribution function, which is the probability of x less than x. So now first question to all of you, which is also defined as capital F of x. Can you tell me how do I first of all define this property? Then we'll come to the Bernoulli random variable. This is more intuitive for continuous distributions, but we'll do it. Yeah.
Summation of all the values Px.
Okay, all the values such that it is less than x, right?
Yes, yes.
Trishanjit. Okay, so which means that let us write it down once and then you'll understand. So from definition, so you seeing the random variable is taking values less than up, still to make it easy for you to understand, let's not write small x for the timing, let's write for once a. So x for all the omega belonging to the sample space such that x of omega is less than a. Yes or no? This is what a CDF is defined as, which is also means that probability of, can you tell me, minus infinity to a. Yes or no?
Yes.
This is how you define a CDF, minus infinity to a. All values a random variable can take, because this less than a means any values between minus infinity and a are permissible for the random variable. So let's take an example for the Bernoulli. So if I told you to plot the distribution of the Bernoulli CDF, when I say distribution, I mean CDF. What would it be? Can anyone tell me? So let us take three cases. Case 1, when a is less than 0. Right? So always remember this diagram for a Bernoulli that I have drawn over here. So the P set is 1, the P complement set is 0, and only two outcomes of the random variable are possible. The random variable can take only two values. So if I ask you a is less than 0, then what is the probability that x is less than a? Can you tell me? So 0 and 1 and 1. Say, let us take minus 0.5. Are there any values for which x becomes less than 0? For
No.
any
No.
samples? No, right? So this is when A is less than 0, this is equal to P of phi, yes or no?
Yes. It will be 0.
Because it will be 0. So anything less than 0. So this, remember that the CDF is a continuous, it's a R to R function. So it will be defined for all R. Similarly, if X is between 0 and 1. So not X, A is between 0 and 1. So probability of X less than A, case 2. What will it be? Can you write it step by step? Someone tell me step by step, what will it be? Do you agree this is going to be X inverse minus infinity to A? Yes or no? Right? And which is the only value for X for which there is an event associated with it?
0.
Good. So we can write this as X inverse 0, which is equal to probability of A complement, which is equal to 1 minus probability of A, which is 1 minus P. Yes or no? Now, if A is greater than 0, what will you get? Greater than 0, no, greater than 1, sorry. What will you get? Can you tell me? So this is going to be X
1.
inverse of 0 and 1. So both are exclusive because inverse maps would be exclusive. So you get probability of A complement plus probability of A, which is equal to 1. Good. So done. CDS also explained. We'll do this in more detail next time. But
Dada, will
now
the
let us
case P be A
Yeah.
more than 1 or A more than equal to?
Equal to 1. Sorry, I drew it in the graph, but I forgot to put it. You're right, absolutely. Somudeep, right?
Yes, Dada.
Okay. Now let's get into binomial distributions. So a binomial distribution is defined as the number of successes in n trials. So for example, I just defined a little bit before. Say I did 50 coin tosses. The binomial distribution will tell me how many of them are heads, right? So this is where I will be bringing you the idea of how to use distributions or random variables to write other random variables. So here X is said to be binomial NP if the number of successes out of n Bernoulli P outcomes is here X measures the number of successes in a when n times the same experiment is done. So what does it mean? Let us write it down. So X is equal to, I'm going to write it down as X I1, I2, I3, and In. Then X is binomial NP if and only if Ij's are distributed as Bernoulli P random variables. So these are called IID random variables. Again, this is the new term. Keep it in mind. IID means independent and identically distributed. Fine. Okay. So now I ask you the question. So if X is equal to the sum of 1 to n, what is the probability that X takes the value? This is the CDF. Please find it as your homework and upload it into the Teams group. We'll have a discussion. It's a repetitive process. You can write it and add it to the group. But let us understand the PMF. So if I say that the probability of X is equal to K, which what does it mean? Can you tell me what does all of these can take? What values can Ij take? 0 or 1, right? Because we are measuring number of successes. So the sum of all the successes is going to be the total number of successes. Yes or no? Okay. So if there has to be k successes, how many of them should be equal to 1 and how many of them should be equal to 0? Can you tell me? K can be between 0, 1, 2, n. If there is any question, please feel free to stop. We are getting into the meat of the day.
K1s and n minus k zeros.
So k ones and n minus k zeros is the idea. So if you have to get, so now k ones means since these are independent processes. So I can say that, say I1 equal to 1, I2 equal to 1, Ik equal to 1, Ik plus 1 equal to 0, dot, 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 In equal to 0. So can you tell me, can anyone tell me what is the probability of this going to be? Independent events can be producted out, right? So I1 equal to 1 to the power k and probability of I1 equal to 0 to the power n minus k. Any questions? Since here I1 and I2 and all are identical. So I can replace ij's with I1 only. It's as if the same coin is being tossed. Like tossing 50 separate coins is the same as tossing the same coin 50 times. That's the idea. So this is p to the power k, 1 minus p to the power n minus k. So, but is this the only outcome? Is this the only way I can get it? See, I put I1 through Ik equal to 1. I could have also put Ik plus 1 equal to 1. Yes or no? So it's basically arranging k ones and a list of zeros. How many ways can I do that? N minus k zeros. Very good. So if you have, if others, if you are not, you don't remember, I'll just give you a quick recap. So there are n factorial ways to do a permutation, and there are a group of n minus k zeros. So you rescale it with n minus k, and there's a group of k ones. So this is defined as n choose k. So you're basically choosing k of the n variables to be 1 to remember. So this is going to be n choose k into p to the power this entire equation. So first of all, what is the, let us check if this is a correct random variable or not. So how, or a correct mass function or not. Can you tell me how can I check if it is a correct mass function?
ওটা ইন্টিগ্রেশন মাইনাস ইনফিনিটি টু ইনফিনিটি 1 হবে।
Yes, is it correct? So we can check this is a discrete random variable k equal to, so the summation over k equal to minus infinity to infinity, x is equal to k. That is all the values the random variable can take. All values that is equal to 1. I leave it to you for homework. Why is this true? This is your homework. And you have to prove it to me using events. Prove using events. This will be a very interesting discussion. Please go ahead and do it. I have done all the ingredients for you to prove that. So this is summation of k equal to 0 to n, because negative values and more than n values are not possible in a coin tosses. N choose k, p to the power k, 1 minus p to the power n minus k. Do you recall this series? Do people recall this series? I would
Binomial
love.
theorem.
Yes.
It's the binomial theorem. So it's p plus 1 minus p to the power of n, which is equal to 1 to the power n, which is 1. That is correct. Fine. So now we understood distributions, we understood a random variable, but that's not enough. When we are doing calculations on random variables, the primary thing one needs to do is to understand an expectation of a random variable. What does it mean? So for example, if I do a coin toss, if I go and do a coin toss in a cricket match or any match before that match starts, if I always say head, how many times am I going to get a success? That's the idea. So you can intuitively tell me that is half of the number of times I toss the coin, right? So that's an expectation of that you have out of a random variable or a distributions, whatever you are talking about. So we will try to formulate it again. This is another definition. Random expectation is again defined, but it is not defined out of thin air. I'll try to give you the reason of the definition. Say normally an expectation of random variable means the average value the random variable takes. See, once you made it in a random variable, things become very simple because you can now do computations like averages. So for example, like you have a list of ones, 3 twos, and 4 threes. So if I ask you the averages, what will you tell me? You will tell average of the series, average is equal to 1 into 2 plus 2 into 3 plus 3 into 4 divided by 9, right? Yes or no? This is what you will tell me. So this is also equal to 1, 2 by 9 plus 2 into 3 by 9 plus 3 into 4 by 9. So now if I said that these were outcomes of a random variable, could I write this as k into probability of x is equal to k and sum over all k's? Yes or no? Because 2 out of 9, I am assuming is the probability that I get ones. This is probability of x is equal to 1, probability of x is equal to 3, 2, and probability of x is equal to 3. Is this clear to everybody? So it's basically weighted averaging with every value the random variable takes into the probability of it. So let us read. Is this derivation clear or is this intuition clear? Yes. Okay.
Yes.
So it's like all values a random variable takes and the probability of taking that value. So it's like a weighted average, basically, nothing else. So let us, if you understood, tell me what is the expected value of a Bernoulli random variable. Can you tell me? Okay, P you say. So P because K is equal to, so the Bernoulli P can take either 0 or 1. So 0 into probability of x is equal to 0 plus 1 into probability of x is equal to 1. This goes to 0 and 1 into P that is equal to P. Very good. Now let us understand some other properties of expectations in general. So first of all, we'll understand what is linearity. So this is a very, very nice property. Let us first use this and get done with one question, and then we'll go to approving it rather. Okay. So, okay, it's defined, it's told afterwards. So let's do it in this order itself. So I'll do this expectation of Bernoulli. I would expect you to do the variance. This is your homework. The variance of the. I will write it down, but yeah, you'll do it as your homework. Fine. So let us do linearity of expectation. So what does linearity of expectation mean? Say you have a random variable x plus y. So this is one random variable. X is a random variable, y is a random variable. One RV, one RV, separate RV. This tells me that if I take the average of the sum, it is essentially taking the sum of the averages, which is making a lot of sense, but it is a difficult proof to do. So let's do it. So let's say z is equal to x plus y, right? This step is clear. So z is a random variable. It's a sum of two random variables. Yes or no? Okay. So now if I tell you, so you are finding expected value of x plus y is equal to expected value of z, which can be written as summation of z's probability capital Z is equal to, let me write cursive z, fine, over all z's that it can take. This is fine for an expectation. I just wrote the definition. So now, can you tell me what can I do? This is why I remember the law of total probability. I can do something here. This is known as the heart of statistics, or that is conditioning. So I know Z, but I don't know X and Y individually. So I have to bring in X and Y somehow. So can you tell me how I bring in X and Y? So I can do something like this, can I? So probability of Z is equal to Z, and I sum over, say, all values of X. Do you agree? This is like summing over all events of X, right? So maybe you will, we did it for the cancer case as well, right? It's the same thing that I'm doing, which is same as Z summation of X, probability of Z is equal to Z, it's not small z, given X is equal to X into probability of X is equal to small x. Is this fine? I am using just the conditional probabilities and law of total probability. Is it clear to everybody? If you have a question, please ask. Okay. So now if X is equal to X, I already know, given that the value of X is equal to X, what is going to be the value of Y, if you have understood? Tell me. Can you tell me? What is Z? Z is X plus Y. If X is already told to be small x, then what is Y going to be?
Z minus X.
Z minus X. This is over all X. Okay. So Z minus X again is defined as, let us define this as Y, small y. So this Z can be written as X plus Y. So I'm going to write both the summations with X and Y. Probability of Y equal to Y. Probability of X is equal to X. So now clearly this can be written as X, probability of X is equal to X, plus summation of Y, which is expected value of X, plus expected value of Y. Fine? Clear? Any question with any step? So I skipped one step over here. So when I take the summation of P of X, X is equal to X, I would be left with a summation of all Y's, Y equal to Y, which is equal to 1, right? Yes or no? Fine. Okay. So linearity is done. The other rule that we have is known as the law of unconscious statistician, or the Lotus rule, which says that given a random variable X, a function of a random variable f of X, the average value of that function is essentially the same thing. You replace X with f of X. So you replace. So again, when you're replacing X with f of X, you get the expected value of a function. So instead of just the function itself, or instead of just the value of the random variable itself, you take the function, you take the random variable, pass it through the function, and you use that to compute the expectation. So can you tell me, anyone, how will we prove that it is true? So let us prove it for a 1-1 function, and then we'll see. how to do it for many to one. Let us do it for 1-1 function. Anyone? Okay, so let us take y is equal to f of x. So can I write? So these are random variables, remember? So now y is equal to f of x. So I can write the expected value of y is what you need, which is expected value of f of x. What is it equal to? Y, p of y is equal to y. Yes or no? Do you agree?
Yes.
Okay, so now can I write this as? So if it is 1-1, f inverse of y is equal to x, right? So I will write this as f of x, probability of f of x is equal to y over all x. Again, let us, yeah. For the time being, let us keep this summation. I'll put in the values. Let this keep this as y for the time being. Okay. So now f inverse of y, x is equal to f inverse of y, and this is y, right? So this is equal to your small x, right? So I can write this as x is equal to small x, f of x over all x, which is what we had set out to prove. Just look at this. Yes or no? So we'll take an example and it will be very clear how are we using this. So this is how you prove. Now for many to one functions, can you tell me how do I extend it? Can you tell me? So there will be a lot of y's, right? So f inverse y will be x1, x2, and so on. It can be a lot of set. It can be more than one value, right? Let us write this as xy, a set xy. So now can you help me with do this? So what would this equation turn out to be? This will be the same equation, right? F of x, which is same as y always, but in the internal, you will have a x belongs to x of y. Yes or no? Because it will not be just one value. It will be multiple values. Yes or no?
Yes.
Fine. Then this can be summed over. So if we put this currently as y, so this can be summed over all the x that belongs to x of y. Probability of x is equal to x. Do you agree?
Yes.
Yes or no? So now this thing, you can just take it outside. Both the summations will be giving you all values of x because there is a redundant term. X's are still the same. So a summation of x belong to xy. So this should be xy for my, sorry for my sloppiness. F of x, p of x is equal to x, which is again, this summation is all values of x in the original variable. We just like, say if we had a set like this, these put random variable to 0, this put it to 1, and the rest put it to 2. So we first took a summation, we set it to 0, 1, 2, and then for all the elements in that set, I take a summation over here. So that's what you are doing, but essentially that turns out to be the same equation. So now using these two properties, let us prove a couple of theorems and then call it off a day. So first of all, let us prove Bernoulli P's expectation. So number one, what is the expected value of binomial random variable? So can I write this as Yes or no? The sum of all the random variables. Because we remember x is equal to I1, I2, dot, 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 In, where n's are IID random variables. So can you tell me what is this going to be? Summation of expected value of j equal to 1 to n. So what did I use to get this? Which property? Linearity, right? And what is the expected value of every Bernoulli random variable, which we saw just now? I think somebody told me, which is equal to P. This is equal to NP. Any questions? This is fine. Okay. So now, since we understood what is the value for this Bernoulli random variable, let us see one more property of binomial we saw. Let us see what is the variance. So currently we saw, say this is the values that a random variable takes. Say these are the heights of a class, heights of students in a class. And this is the number of students. So you know that this is the mean height, but mean is often not the best measure. So you want to see how far away are you from the mean, right? So the best way is on expectation, how far will you be away from the mean? So that's how you define it. So people may have defined it this way. But can you tell me why can't we define this using expected value? So this, do you agree? This is x. This is the expected value of x. This is the distance, which is x minus expected value of x. But I can't use it directly as a measure. Why? What is expected value of x minus expected value of x? By linearity, what can I write? Please, if you don't follow, please ask. So now this is the expected value of x. What is the expected value of x? This is a constant, yes or no? The expected value of a constant, the expected value of x is the constant. The expected value of a constant is, what will it be? This is equal to 1, is equal to c. So this is turning out to be 0, which I don't want, right? That's the basic problem of this. So that's why people define variance as expected value of x minus expected value of x whole square. In the mean, in the positive sense, how much is it far away? In the absolute distance sense. So can I write this? How can I write this as the expected value of x square minus 2x expected value of x plus expected value of x whole square. So what is this going to be? Can you tell me? The first term is going to be expected value of x whole square. Then you have 2 into expected value of x whole square plus expected value of x whole square, which is equal to, right? Let us do an example and understand, but is this step clear? The second term is expected value of 2x expected value of x. So 2 into expected value of x is a constant which can go outside. So you get 2 expected value of x into expected value of x. This is how I got this squared term again. So now let us find it for a Bernoulli. You can do it as a homework for binomial by independence. You will add all of them separately. I already did it. But yeah, the variance of a Bernoulli P. What is it going to be? So let us find out expected value of x squared minus expected value of x whole square. So what will be expected value of x squared? I will use Lotus. Tell me, how can I write this as? summation of x squared, x is equal to x is equal to 0 and 1, minus I know the expected value of a Bernoulli random variable, that is p, which is probability of x equal to 1 minus probability p square, which is p minus p square, which is p into 1 minus p. Is it clear?
Yes.
Okay. So the final thing for today, I'll just derive and then we'll call it a day, is a geometric distribution. I've also a homework for you, which I did last time. Pause on, but I'll not do it because it's not relevant for RL. But yeah, you can do these two homeworks and come to next day. So they find the variance and the expectation as homework. And I'll do this memoryless property as an interesting property. Okay, so the geometric distribution says that it is the number of attempts required to get a first success. For example, you keep on playing or you keep on giving a driving license test unless you get a success. That is a geometric distribution. So if I tell you where each of the, so it's like a set of IID Bernoulli random variable, but you wait till you get the nth value, which is the success. So can you tell me what is the probability that you have to wait for n values, which is n greater than equal to 1, 0 otherwise. You at least need one value to get a success. So for getting a success, what should be the list? Say you get a success at n trials. So it should be list of failures, right? First, n minus 1 failures and 1 success. So what is the probability of this? Can you tell me? Probability of failure is how much? 1 minus p. Probability of success is p. So probability of taking n out n times is how much? N minus 1 failures were followed by 1 success. Is so it's 1 minus p.
1 minus p
Yeah,
to the
go
power
ahead.
n minus 1 into p.
N minus 1 into p. This is equal to 1 minus p to the power n minus 1 into p. This is the PMF. You can try out the expected value, but let's do one interesting property before finishing off. So the property of is called memoryless property. So it's very simple to a coin toss. It says that, say people are talking about in if they talk in sport that the captain who lost 14 tosses in a row, by law of expectation, he should win the next one, because at the end of the day, it should be 0.5 should be the output of a coin toss. But I'll show you that since the coin tosses are independent, given that 15 tosses are head, does not mean that it will take you lesser time to get the next success. Like given that 15 coins are tails or failures, it doesn't mean that the next one is going to be a success guaranteedly. It is same as starting refresh. So which means that say you have already tossed m times. This is m plus n. The memoryless property says that, say if you have to get success after m plus n, it is equivalent to starting at m itself. So this is n. So m plus n, given the number of failures is m, is always is equal to this. Let us try and do this. So probability of x greater than m plus n given x greater than m. What can we write this as? We can write this as x greater than equal to m plus n, comma x greater than m by probability of x greater than m. Yes or no?
Yes.
Okay. So now I tell you that x is greater than m and x is greater than m plus n. What does it mean? What is the intersection of these two events? X is greater than m and x is greater than m plus n. What is the intersection?
It's greater than m plus n.
X is greater than m plus n.
So now let us take what is, let us find out. So once we find out one, the other ones all will be very simple. So what is x greater than m? Can you tell me what is x greater than m? So I equal to m plus 1 to infinity. P of x is equal to I. Yes or no? This is what the probability of x is greater than m means, that you can take m plus 1 outputs, m plus 2, m plus 3 trials and so on, all the way to infinity. Yes or no?
Yes.
Right? So now each of these can be written as p to the power I minus 1 into p summation I equal to m plus 1 to infinity. So if I take p to the power m common, right, I'll get what will I get? Sorry, 1 minus p, sorry. I'll get. So let me write this down once. So I'll get 1 minus p to the power m, p plus 1 minus one moment, plus 1 minus p to the power m plus 1 p and so on. So I'll just take 1 minus p to the power m common into p. What will I get? I'll get 1 plus 1 minus p plus 1 minus p square dot dot dot. So what is this value? Can you tell me?
1 by p. 1 by p.
This one. So 1 by 1 minus p into p. So this gets cancelled. So it is equal to 1 minus p to the power n. So the numerator is greater than equal to m. So what will I have? I'll have one more extra term, right? Let us write it down. So this can be written as x greater than equal to greater than m plus n minus 1 by probability of x greater than m. Yes or no? Fine. So what can I write this as? Can you tell me? 1 minus p to the power m plus n minus 1 by 1 minus p to the power m. Yes or no? Because I got it for all k. If you are confused, how did Dada do it? I got it for all k, right? Fine. So now this is equal to 1 minus p to the power n minus 1. Fine. Which is equal to probability of x greater than equal to n minus 1, which is equal to probability of x greater than equal to n. Fine. I hope this is clear. So what did I want to make a point? That given that m failures have happened, it is same as starting from scratch, as if m equal to 0. For success. If it is a geometric distribution, the starting from scratch is essentially equal to already observing that m failures have happened. This is known as the memoryless property. Every time you get an output, the geometric distribution or the exponential distributions reset themselves. So that's the memoryless property. That's why when they say in media and in sports channels that he has failed so many times by a law of large numbers and so on, law of statistics, it should not get success. It's not right. That's a different debate in itself. You can't infer anything about the future given the past information you have already got. Okay, so any questions do you have? We'll stop here and please do the homework that I gave for like the proving that the summation equal to 1 and so on. I'll upload this, the video as well as the annotated notes, and this Poisson distribution also similarly find it out. And we'll meet on Wednesday at 8 again. and we'll do continuous distributions. So 2 more classes on probability before we begin with RL. So any questions in particular, anything you want to ask?
Hello, Moinagda. I am
Yeah.
Shaptoshi Upadhyay, an IT UG1 student. Actually, I was facing some problems regarding joining that Teams group.
Okay,
And
I'll take that in some time. It's recording. I'll just stop recording and take that. Any questions related to class? Okay, if there's no questions, we'll please upload the solutions onto the Teams group in the discussion, and then we'll just discuss from next day. So I'll stop recording.